Okay, let's start. Here, let's do this example. So we're doing Taylor and Maclaurin series. Taylor and Maclaurin series. There's kind of two kinds of problems that you do with these. That is, you build them from scratch. And that's what we're going to do right now. We're going to build this from scratch, where we actually, well, let's write, so what is the general, let's write down the general formula for a Taylor series. What is that? So a function f can be written as a series, and do you remember what it is? So it's not to the n, that's the nth derivative taken at, oh, that's Maclaurin. So whatever you're centering about, so yeah, Maclaurin would be a or 0, but Taylor is just any a, and then x a to the n factorial. So that's our Taylor series, right? That's our Taylor series. And if this thing converges for a particular value of x, that means it will converge to that value of x of the function. But if this, for a particular value of x, if this series converges, what does it mean about the sequence? What does it mean about the sequence? The sequence must go to 0, right? Only chance for a series to ever converge is if the sequence goes to 0. All right, so that's true for Taylor and Maclaurin series too. For any value of x for which it converges to your function value, that sequence of values would have to converge to 0, and also converge to 0 fast enough, right? And that will always be true for the Taylor and Maclaurin series wherever it converges. Okay. So we're going to do this one. So our a value here for our function that we want to do then is natural log of 2x. And our center point, we're going to center around x equals 3. So that's the example we're going to do. And we're going to build this from scratch. Okay? We're going to build this from scratch. Okay? So if we build it from scratch, we're looking at this. And the only thing these we just write down. So x minus 3 to the n, piece of cake, we just write it down. And factorial, we just write it down for each term. Here's where the work is, where we have to do. Is we have to find these different derivatives of natural log of 2 evaluated at 3. So in terms of building the series from scratch, that's where the work is finding all these derivatives. So we make a table for that to help us. And so we're going to look at n equals 0, 1, 2. We'll see. We'll just start by writing down 5. We'll see. And basically, we just need to go far enough to get the pattern. Once we develop the pattern, then we can write the general formula for this, and then write out as many terms as we want. So what is the 0th derivative, which is just the function itself? That is natural log of 2x, evaluated at 3. Natural log of 6. Okay? So then when n equals 1, we're going to have the first derivative of natural log of 2x. What's the first derivative of natural log of 2x? Could be 1 over 2x times 2, which is, someone say it louder, it's just 1 over x, right? And that's going to, let's do that simplification, make our life easier as we go on from there. Okay, and then evaluated at 3, 1/3. So this middle column here is solely for the purpose of generating this column, because this column is our values for each term of this right here. So we're finding the derivative and then plug in, and this is the column we're interested in. This is what the series is made up of, or the sequence is made up of these coefficients, or these multipliers. Okay, so second derivative. Negative 1 over x squared. Agree? So you got to see this as x to the minus 1. So negative 1 over x squared. And we get 3 squared. Right? So the derivative then is just going to be negative 1 over 3 squared. Okay? Derivative of this is, so it's going to be negative 1 times negative 2, which is 2, times 1 over x cubed, which is 2 over. Now, in order to build a formula for this, it's easiest to do that if you just keep this unsimplified. Like, don't do any simplification, and as we go further down, you'll see what happens here when you do that. Okay, next one, this is negative 3, so we'll have negative 3 times 2 times 1 over x to the 4th. So again, we're going to write that out. Negative 3 times 2 over 3 to the 4th. Everyone following what I'm doing? So that's a times, not a minus. This is a minus. That's a times. Okay. So now we're going to have negative 4 times all of that, which will make a positive. So it'll be 4 times 3 times 2 times. All right. So then we'll have. So what's happening here? What is 4 times 3 times 2? 4 factorial. So let's just do it. So it's 4 factorial over 3 to the 5th. Okay, then we're going to have negative 5 times all of that. So it'll be negative 5 times 4 times 3 times 2. One over x to the 6th. So now what do we have now? Negative, right? Negative 5 factorial over x to the 6th. And we could we can just guess for now, what's this going to be? This is going to be positive 6 factorial over, 3 to the 6th. This is 3, right? This is where we actually evaluated at 3. So looking at the pattern here, what do we see? We see alternating, right? We see the factorial growing, and we see in the denominator, we see powers of 3 growing. So this column now is going to form this will form our Taylor series. So let's write out some terms. So we're going to have, this is going to equal ln of 6, what, plus 1/3 over 1 factorial times x minus 3. And then we're going to have what? Negative 1 over 3 squared, x minus 3 squared, over 2 factorial. Where are we now? Okay, now plus 1 over 3 cubed, positive. But what is this 2 right here if we start looking at the pattern? It's really 2 factorial, right? So it's like 2 factorial times 1 over 3 cubed. I ran out of room. X minus 3. I'll do it in red. X minus 3 to the 3rd. And that over 3 factorial. So let's just skip ahead. We'll just skip ahead a little bit here. So minus dot dot dot. Let's skip ahead to n equals 6. Okay, n equals 6 will give us minus 5 factorial times 1 over 3 to the 6th times x minus 3 to the 6th all over 6 factorial. So this right here, well, that'll be the last one you do. Okay, so plus dot dot dot. So this one will really help us get that formula, right? So this is for n equals what? For n equals 6. So we want to we're going to simplify this, and we're going to then generalize it for any n. All right. So first of all, what simplifies? What do you see simplifies? 5 factorial over 6 factorial is what? 6. And that works for all of them, right? 2 factorial over 3 factorial leaves 3. You would, then the next one, we'd have 6 factorial over 7 factorial, which would leave 7 in the denominator. So what, in terms of a formula, what is all of that? Just n in the denominator. Good. So just n in the denominator. And then this is denominator 2. This is 3 to the n. And then we have x minus 3 to the n. What else do we have? Alternating. So negative 1. So it's either going to be n or n plus 1. So we get these signs right. So should it be n or n plus 1? So if I have, when n is even, I want negative. So right, n plus 1. Okay, and then when does that pattern start? Is that n equals 0? No, look what happens with n equals 0. Undefined. N equals 1, this is my n equals 1 term, right? Is that right? So that's where it makes sense to start, but that won't be the series. Why not? I'm going to have to add that natural log of 6 in there. No, because we didn't integrate. It kind of feels like that, but we didn't do antiderivative. It's just well, it kind of is because these are derivatives, right? So this is antiderivative, so you have this constant. So it's kind of like that, yeah. Okay.
For a series to be centered around a number.
Yeah, I'm gonna show you that in a second. All right, good question. So now, what's the next question we need to ask? Yeah, so this might not be true for all values of x. When we did e to the x and we did the cosine and sine, those are convergent for an infinite radius, all values of x. Maybe not the case here. So what do we need to do? We got to figure out what's the radius, or what's the interval. We need the interval, and we're going to get that from? Yeah.
Would we need, with the index shift, would we need to change those n's to n minus 1 so that it would be...
No, it wasn't an index shift, because this is still...
Oh, it's just like cutting it off.
Yeah, it's just starting at 1 and then adding this one. So this is still n equals 1, still gets me this, I think. Gets it right. So let's just practice. Let's try it. So when n equals 1, I'm going to have a positive x minus 3 to the first over 3. Yeah, it worked. So I didn't shift the index. I just noted that this pattern starts at n equals 1. We also have to add the element of 6. Okay, so to get the interval, we're going to do ratio test, right? Ratio test. And so we'll have, can I fit it right here? Let's see if I can fit it right in here. That'll be my little challenge. Okay, so x minus 3 n plus 1. We know the negative 1 will just go away. It's in the absolute value. Okay, and then n plus 1 and 3 to the n plus 1 times n times 3 to the n all over x minus 3 to the n. So I'm going to skip a bunch of steps here. We're just going to, what are we going to see? We're going to have a 3 in the denominator. N over n plus 1, the limit will be, what will the limit be? N over n plus 1. Super easy. That'll just go away, right? The limit will be 1. I'll have one more 3 in the denominator and one x minus 3 in the numerator. So we're going to have x minus 3 all over 3 has to be less than 1. So I skipped steps there. That would not be good practice. You want to show the limit notation along the way, show evaluating the limit, but then after you evaluate the limit, you get this right here. You have one more x minus 3 in the numerator, one more 3 in the denominator, so that thing has to be less than 1, which means that x minus 3, again, skipping a step here, has to be less than 3 and greater than negative 3, which means our interval is from what? 0 to 6. And what do you notice? That's the center of that interval?
At A.
A, right? So yeah, so their center, look, notice, here's the first thing we see. It's convergent for all x values from 0 to 6, and notice that our center is at x equals 3. And that's the center of our interval. So outside of less than 0 or 0 or less and greater than 6, this will not hold for ln of 2x. But for all those x values, this right here, series, represents the function ln of 2x. Unless we'll take a look at that in a second. Questions on all the math? Did you follow? Okay, so let's look at this. Can I erase? Okay, so here is ln of 2x. There's the graph of it. And then I've written out, is this what we got? So I got ln of 6 plus n equals 1. So I did negative 1/3 to the n and then the opposite. So that altogether is the same as what we got. Negative 1 to the n times 1/3 to the n. X minus 3 over n. So are these the terms we got? They should be. Okay, they should be. So what we can do to see how this works is we look at partial sums, right? The first partial sum is just natural log of 6. Just natural log of 6 is this. Okay? So is this a good approximation of ln of 2x? No, certainly not a good approximation of ln of 2x, but what does it have correct? At 3, right? At x equals 3. At x equals 3, what do you get? You get the natural log of 6. And there it is. So just taking that first ln of 6, it gets it right for that one value. And that's our center point. John?
Did we have the negative 1 at n plus 1?
Yeah, well, that's right here.
Okay.
Yeah, so when you put all that together, you get the same thing we did. Yeah, so yeah, there's another negative sign here. So, yep. Okay, and so now if we take the first two terms, which would be ln of 6 plus this term right here, this is the second partial sum, the ln of 6 plus, there you go. So what does this get correct? It gets the function value correct at 3, and it also gets the rate of change at 3, or the first derivative at 3. Those are both correct, and so that gives us a good approximation close to 3. Add one more term, so this is the first 3 terms now. Here's the first 3 terms of the series. The red one, right, the blue one is the function, the actual ln of 2x. The red one is our partial sum, the first 3 sums. And so you see now it's curved, first 2 derivatives are correct, and it's now starting to really hover around 3 It's starting to do a really good job hovering on the curve there. You can't really see any daylight for a pretty good range there. And as we keep adding more and more terms, what's happening? It's converging, but only between what? 0 and 6, right? So this is going to only work for 0 to 6, so I can add terms until I'm blue in the face, but it's only going to converge in this interval right here. And so watch what happens to the right of 6. So I'm going to keep adding terms. Watch what happens to the right of 6. So here's the first 12 terms, 13, 14. So to the right of 6, that red function is never going to hover to the ln of 2x graph. It's just going to keep flipping up and down. So there's the first 20 terms. The first 20 terms gives you this. Oh, let me take the book. Gives you this curve right here. Which is an excellent representation of ln of 2x from 0 to 6. But as soon as you get off of 6, it just diverges, right? It spirals off. And also, this is not defined less than 0, at 0 or less than 0, but this is. And so it's trying to show you more, but that's not there. So I'm showing it again, the original function. So Taylor series this is really cool because you can start with any function and you can make a polynomial that essentially replicates the function. As for sine curves, exponential, logs, we're building polynomials. Building a polynomial with an infinite number of terms that replicates that function within the radius of convergence. Okay, and then the partial, so like this is the first 20 terms, just the first 20 terms of the polynomial, is doing a really, really good job in that radius between 0 and 6, because it's like, see how it's black? It's like it's basically the same thing.
Could you make like a step function of Taylor series that would define the entire thing if you change the if you changed A for each step?
Right. So then, if you came out here for 2x and you centered about what 9 or something,
Mm-hmm.
and then that would build that part of it, and then
Wouldn't it overlap?
what's that?
Wouldn't it overlap?
Oh yeah. So right. So if you came out further, so any a value is going to approximate correctly back to 0.
Okay.
And then right. So we centered at 3. So that goes from 0 to 6. So if you did it around 10, that radius would be like from 0 to 20. So what you really need is you need to get the actual for all values of x. Yeah, like you let your center point go to infinity, and then you'd get it all. Okay. Any other questions on this example? Okay, and so then the other type of Taylor series problem is so building them from scratch, that's something you need to know how to do. But then there's also, there we go. So now here's the other type of problem you see. So here are the most common Maclaurin series. I'm going to post this for you. I thought I did last semester. I can't find it, but so I'm going to post this for you. So we know 1 over x, that's just our basic geometric series. E to the x we did in class. Here's sine x, here's cosine x, I think we did. And then here's tangent inverse. So these are the most common Maclaurin series, and then their radius of convergence. And so then you get problems like this. You could say like, write a Maclaurin series for the square root of x times sine of 4x. So what about building that from scratch? What would happen when we build that from scratch? Yeah, and then as we're using the product rule, it's just going to blow up because it's going to keep expanding out. We're going to get 2 terms that are product, then 4 terms that are products. Okay, so rather than do it from scratch like the one we just did, we can use the known series for sine x to do this. So if sine x is this right here, then what is square root of sine of 4x? Can you write it down? So just the first step, can you write down what square root of x times sine of 4x is? If that's sine x. Try that. So we're going to use the one that we know to just simply write this one down. So what do we have? Instead of x to the 2n plus 1, we're going to have 4x. So it's the idea of function, right? That this function is whatever you have for x, you're going to do for x here. So it's going to be 4x to the 2n plus 1. And then we'll also have an additional x to the 1/2.
Just do 3 halves n plus.
Yeah, so now we'll simplify this. So we'll have negative 1 to the n. And let's get this 4 out. So it would be 4 to the 2n plus 1 and x to the 2n plus 1.5, 3 halves. So your exponent of x is 2n plus 3 halves, right? Because you'd be multiplying x to the 2n plus 1 times x to the 1/2. So you're multiplying by another half power of x, or so that would be adding 1/2 to that, all over 2n plus 1. And we know exactly what this means. We could, if we needed to, we could write out the terms, right? It would take time, but just be careful. We could write out the terms, dot, dot, dot. And so this would be a way then, now that we have this particular function written as a polynomial, it would be a way to do something like this. How could we estimate, say, from 0 to pi pi, or something like this? Rather than, especially if this was something like x squared or x cubed, then now we'd have a real problem. We might be able to do this with one of our techniques from the beginning of the semester. Maybe this is undoing the product rule, might work, or something like that. But now that we have a polynomial version of that same function, so we know polynomials are really easy to do antiderivative of. So we could just substitute in as many terms as, and even consider it to keep going.
Is it
Five. So polynomials they're very user friendly, right? They're easy to take the derivative of, they're easy to take the integral of, and so it's one reason why we might want to make a power series out of a function like radical x sine of 4x. If we've got individual polynomial terms, we know it's a simple power rule, right? Just keep all your coefficient and do power rule. So maybe this is easier than an antiderivative of original. So we can take these easy general forms that are given, and we can manipulate them. We can do like transformations of them into other functions. And then we could do derivatives and integrals on the polynomial version rather than the complicated kind of like transcendental version. Okay, these are called transcendental functions. Okay. So does that make sense? So polynomial version of that thing. If we wanted to, if we were asked to do an integral, then we could do it as, right? And what could we do? We could do the first 4 terms, get those antiderivatives, and look for the pattern of that, right? And so, and that would be the antiderivative of this series. Okay, so that concludes what we're talking about for Taylor. Any questions? And that should be good for your homework. Yeah.
Are we going to have Taylor series on the exam?
Yes. Yeah, I think that would put that in the list of problems. So that's fair game for Friday's exam. So basically this exam starts with the sequences to what we just did Taylor series. Everything is in there. Okay, last chance before we start next section. Yeah.
So rather than adding in the x to the 1/2,
Yeah.
if we multiply the entire series by just square root of x on the outside of the sigma,
Yeah.
that also works, right?
It's the same thing. Yeah, because it's just you just end up distributing it. So when you end up writing out these terms, you get the exact same thing.
Is that like proper notation though? Or?
No, you should have all your x terms inside, because you don't want it'd be okay like to pull out common factors, but you don't. It's probably not customary to pull out x's because you want all your x's gathered together. So that's better form. Other questions? Yeah.
You're saying instead of integrating the original square root of x on 4x,
Uh-huh.
you integrate the argument of the sigma, you integrate the first few terms.
Actually, either, right? So we know how to do that. We've done that before, right? So you could write down the terms and integrate them one by one. You could also then integrate this as a general formula, and it should match up.
But if you chose to integrate the terms, how many would you need to write?
So it might be like by the request of the problem that you're doing, or just enough to then rebuild a formula if you wanted to. Does that answer it? Yeah. So there's no magic number. 3, 4. There's 5. There's no magic number to how many. If you were shooting to build it in sigma notation, it'd be enough to gain knowledge of the pattern. Yeah. Other questions? Okay. So let's start the next thing. Just changing gears here. And so the next thing we'll do is parametric functions. So the sequences in series, super important. It shows up a lot in further math. But in terms of Calc 3, this is a big part of Calc 3, is understanding these things called parametric functions. So in terms of getting ready for Calc 3, this next couple weeks is more important for Calc 3 than sequences in series. So in your math career up to this point in calculus, algebra, we've dealt with functions like this. Y is a function of x. For instance, x squared plus square root of x. Independent variable is x. For different values of x, it generates different values of the dependent variable. In this case, f of x. Okay, so parametric functions are different. Okay, so they're of this function, this form. X is some function of t, and y is another function of t. So we're introducing a new variable, and that new variable is called the parameter. Okay, so the new variable and that parameter, that becomes our independent variable. but it's still based on the xy plane because the independent variable, for any given value of the independent variable, t, it generates what? Now, instead of generating one value, it generates two. It generates an x value and a y value. So it's really generating a point in the plane. So every value of t generates a point in the plane. Okay, so and we can just start off with a table of values. This is probably, but maybe the last time we want to do this, but just to get the hang of it. So we can look at values of t and then generate ordered pairs x and y. So when t is 1, we get the point. What do we get? For this 3 and 1/2, right? So t equals 1 generates the point 3 1/2. T equals -1. What does that give us? 1, -1/2. T equals 3. 5 and 27/2. Is that 13.5? And let's just do 0 here. 0 gives us 2, 0. Okay, so we could plot these points easily, right? So 3 1/2. And 5 and off the chart there, 1 and -1/2. And 0, 2, 2, 0. And let's do -2 and 2, just to get a couple more. -2 gives 0 and, is that -4? Check my math. 2 is 4 and +4. So this is now we see what maybe the set of all points is kind of taking shape here. So let's write down this was for t equals -2, right? And this was t equals -1. T equals 0 is here. T equals 1. And t equals 2. So notice that, so all the points are going to generate a curve, right? All the points are going to generate a curve. But different than just a curve of an equation of x and y, notice that there's a direction of the curve, or an orientation of the curve for increasing t. So as t increases, so rather than just having a curve that we think of as x increases from left to right, now we think of t increasing, and then the curve emerging in a certain direction. So let's graph the whole thing. So here's the same thing, right? X is t plus 2, y is half t cubed. And so I'll graph it purple here, maybe. There it is, okay. But so more than just all those points, the direction then is, which is the direction? Is it up and to the right or down and to the left? For increasing t. Up and to the right, right? So we can kind of put some little arrows on here telling us that not only do we get all these points, but they are generated in this direction as t increases. Yeah?
Can I just solve for x and then substitute that in for t and y and get an f of x equation?
Okay, yeah, so you guys go ahead and do that.
That would just be 1/2.
So no, everyone do it. So do you see what he's saying? So could you combine these equations? He's asking, could you combine these equations and get rid of t and get an equation of x and y? Could you do it? There's definitely an easier way and an uglier, harder way. So choose the easier way. So how could you combine these equations to get rid of t, and then you just have a relationship just of x and y, and the t would be gone? You see what you would do? What did you want to do, Corey?
Well, I solve for x, or I solve for t on the x side rather.
Okay.
To get t equals to x minus 2.
All right, that's your hint to start. T is x minus 2. If t is x minus 2, then could you write an equation just of x and y without t's anymore? Without t's anymore. Okay, and what would that be? Yeah, so if t, right, t is x minus 2, then y is 1/2 t cubed. Well, t and x minus 2 are the same thing. So we can do that. And so if I come up here and I say, all right, I want you to graph for me y equals 1/2 x minus 2 quantity cubed, what's going to happen? Same set of points, okay? So it just landed right on top of it. It's the same set of points, whether it's defined as a parametric function or as just our standard function or relationship of x and y that we're used to. But again, this has something, the parametric function has something that this doesn't. An orientation, right? It has an orientation for increasing t this way, okay? So in this particular case, it happens to be the same as if you were thinking of x increasing and what y would do as x increases. But that won't always be the case at all. So this parametric functions also have this orientation for increasing t. Okay, so this opens up the door for some pretty crazy stuff. So let's take a look at some possibilities here. Not that one. It's pretty awesome, isn't it? Let's see, this one. So here's one. X is t cubed minus 3t squared plus 1. Y equals minus 2t to the fourth plus 3t squared minus t plus 4. So they're both individually polynomials. And we get this. And we're actually, after we get through the basics, we're going to be spending a lot of time doing all kinds of analysis on this particular function. It's a really good example for looking at different, when we get into the calculus of things. Okay? So, is it a function? Is it a function?
It's 2y.
Okay, that's the right question, right? Is y a function of x? So that's the question you're answering. Is y a function of x? Is it? No.
T is a function of x.
Okay. So for given value of x, do we get just one y? No, there's lots of examples here where we get more than one value of y for given x. So when you said no, you were answering the question, is y a function of x? Which is true. It is not a function of x. But what you're looking at, is it a function? How could it be thought of as a function? Independent variable is t. Dependent is an ordered pair, x and y. Given a value of t, do you only get one ordered pair, x and y? So for every value of t that you choose, do you get just one distinct value pair, x and y? Yes, you do. So in this perspective, it is a function. For any given t, you get just one corresponding ordered pair, x and y. That's the function. if you consider independent to be t and dependent to be an ordered pair of values, then that is a function. Yeah, please.
So that means that t itself is not represented in the axes.
It's invisible, right? Right. It's behind the scenes, right? It's generating this curve, but behind the scenes, we don't graph the value of t. Exactly. We end up still graphing a set of ordered pairs x and y. That's precisely right. Okay, some more good ones here. And we'll call it a day. Okay, so we can get all the kinds of things like we saw a cubic. Here's an example of a quadratic. X is 1 plus 3t, y equals 2 minus t squared. That'd be easy to, again, solve for t in x, plug it into y, and you get a standard parabola. Okay? Here's cosine t and sine of t plus sine of 5t. That's cool. Here's one more fun one. There's t plus, so it's not that complicated, right? So t plus sine of 2t, t plus sine of 3t. It's not a super complicated in terms of each one individually, but then if...
Wait, is that giving you 2 points for, is that a function? Because that has two, it's intersecting with itself.
Yeah.
It has 2t that are 1, x and y.
Okay, so you're asking the question, thinking back easier. You're asking the question you're saying, is this a function? You're saying, I got 2 different values of x that give me the same y.
All right. Well,
Is it a function?
When you put it like that.
Yeah? That's the same situation though, right?
Yeah, it's true.
2 different values of t are giving the same ordered pair. Is that okay? That's
It's
perfectly
just
okay.
represented differently, which is
Right, but that's the same situation. So for given value of t, you get 2 different ordered pairs. No, sorry. For 2 different values of t, you get the same ordered pair. That doesn't violate a function. It doesn't violate a function. Okay, homework, WebWorks due Wednesday.
There any super
Maybe. There might be a short one. There might be an additional short web work on this stuff.